Hi, thank you all for joining us for the last session of today. My name is Angela, and I'm a software engineer at Pivotal.
I'm Nitya. I'm also a software engineer at Pivotal.
We're both members of the R&D networking program, where we work on all things networking and routing related for Pivotal platform. And today we're talking about debugging the Cloud Foundry routing tier. So a brief overview of what we're going to be talking about today. We're going to start by talking about what exactly, this always happens. Start by talking about what exactly the routing tier is, so we all level set on what exactly we're referring to, the different components, especially because as we talk about debugging, it's important to know where things can go wrong. Before diving into two case studies of real issues that we've encountered as members of the networking program that we've had to debug. By going through these case studies, we hope to show two different methods you can take towards debugging problems, as well as introduce you to a variety of tools that you can use when debugging problems in the routing tier. And then we're going to cap off with additional debugging tips that we may or may not have been able to cover in either of the two case studies. The goal is that everybody in this room leaves with a couple of different things in the back of their mind. First, hopefully, everybody leaves with an understanding of debugging as a process. Hopefully, debugging isn't something where you just sort of go cowboy anymore. You have a methodology behind it, and you can apply it whether or not you're debugging something in the Cloud Foundry or Pivotal Platform routing tier, but to any other problems that you might be encountering in your day-to-day work. But of course, since we are talking about debugging in the CF routing tier, we also hope that you leave with a high-level understanding of all of the components involved in the routing and networking layer. And with that, I'm going to hand it off to Nitya to talk about what exactly the routing tier is.
Cool. So I'm going to talk about what the routing tier is and how it fits into the rest of Cloud Foundry. So in this diagram, the gray box represents the system components of Cloud Foundry, like the API, Diego, UAA, and your routers. And the components that the gray box represents all make it possible to CF push and run your applications. And all of the colorful boxes are components of the routing tier. So in a typical CF deployment, your routing tier may have your load balancer, HAProxy, Go router, or TCP router, and your applications. So if we just look at the left side of this diagram, we can see all the components that an HTTP request would go through before finally being routed to an HTTP application. So the load balancer is the front-facing part of your CF, and it'll be the component that receives the request, and it will forward it to the HAProxy. The HAProxy would be configured to point to the Go routers as its backends. And you'd tend to use HAProxy in a deployment when you need features offered by HAProxy that aren't offered by your load balancer or your CF routers. So for example, HAProxy allows you to define access control lists. So then you have Go router. Go router is a layer 7 HTTP router that handles connections to your application backends. So it has a series of handlers that will run and process your request before it then makes a new request to the backend. And it can also route you to other CF components like the API. And ultimately, you reach your app. So now that you have this overview, we'll talk about some problems that people have encountered running CF in production. And we'll go through some specific case studies and also some general debugging tips. So I'll give it over to Angela.
Great, thanks, Nitya. So we're going to go into case study number 1. And oftentimes when problems manifest in the routing tier, it's impacting your production systems. You have applications running, the apps are no longer reachable, things are down, prod is down. That's really scary. And so as members of the networking program, we oftentimes get pinged and paged with the problem statement that's something like, the Go router's broken. We're all panicking, right? Like, prod is down, that's not a good feeling, and you need to figure out how to help us get it back up. And while this is totally understandable as a reaction to a fire being lit It's definitely not the most helpful in actually figuring out how to go about debugging. And so the first thing we recommend, this I know seems silly, but as we go through sort of the debugging steps that we like to take into account, the first thing we like to do is state the problem in our own words. This is useful even if you're the one who's encountering a problem, to just write down what the problem actually is to better understand it. And even if somebody comes to you with the most well laid out explanation of an issue that they're seeing, it can be really useful to take what they're saying, write it in your own words, and present it back to them to make sure that you are on the same page. You've level set on what the actual issue is, what's being affected, and the components that are involved. So in case study number 1, the problem statement that we came up with, and I know this is a wall of text, but bear with me, is that the customer had 2 microservices deployed in their Cloud Foundry installation. One microservice was externally facing and was sending CRUD requests to a second known as internal application. The front end, the externally facing microservice, on an incoming GET request would send a GET to the back end, immediately followed by a PUT request. The GET request would always succeed, but the PUT consistently errored out. Now, again, I realize that this is a wall of text, and another thing that you can be doing when stating the problem statement is also to visualize what it's actually meaning. I know personally I'm a very visual learner, and so let's actually take this and diagram it out. So in this case, we can think of it as having the Go router, a front end, and a back end. The GET request would come in, the Go router would know to forward it to the front end, and the front end, based on this GET request, would then send a GET request to the back end. In this case, they weren't using container-to-container networking, so the request was actually hairpinning back out and in through the Go router, was being sent to the back end, and the back end was successfully responding. And then the front end would send a PUT request. And this is where things are a little fuzzy, right? We know that an error is occurring, but is it occurring at the Go router? Or is the Go router successfully forwarding the request, and the back end's what's actually causing the PUT to error out? Who really knows, right? That's why we're debugging this problem. This is further compounded by the fact that we're not just dealing with these 3 boxes. These are just some of the components in our Cloud Foundry installation. As Nitya pointed out when we were level setting on what the routing tier is, we also have additional components, such as the load balancer and HAProxy, to take into account. And so instead of thinking of it as 4 network connections that we need to be concerned with, we really have 8 network connections, multiple places where things can be going wrong. And so this is where the second step in our debugging process comes into play, that we want to level set on the architecture. In this case, the architecture of the client was pretty straightforward. It was a load balancer forwarding to an HAProxy, to a Go router, and then to your application. At this point, you might say, great, I know a network connection problem is happening. The PUT is erroring out. I know the architecture. You're really eager to solve this because it's impacting your prod systems. And you really want to just jump in and figure out the connection that's failing. But we recommend staying in the information collecting phase, and that's what we did in this case. In addition to level setting on the architecture, we also level set on the configuration of all of these components that were in the network path. So in this case, we gathered configuration information about the load balancer, HAProxy, and Go router. And so by doing this all up front, we're not going to bias ourselves later to only asking for certain configuration of specific components. The configuration we gathered about each of these different components included a variety of different timeouts, which is important when you have network connections that are erroring. You can also get a lot of this configuration by just SSHing onto all the Bosch VMs and looking at the config files on those disks. So now that we've gathered the configuration, the third step we want to take, and I say this a bit cheekily, is you want to go ahead and gather even more information. This is a pretty broad statement, right? Like you're like, I've already gathered information. I've level set on the architecture. I've like know all the configuration about all the components. Like, what do you mean? Like this is pretty broad. But again, it really depends on what problem you're facing. So depending on the scenario and the issue, the problem statement, you might be more likely to gather some information than others. So in this case, the customer actually noticed the problem by looking at the application logs to begin with. They saw an IO error on the put request. And so as part of it, logs are generally a good place to start. And so in addition to gathering all the application logs, we also gathered the logs for the load balancer, HAProxy, and GoRouter. Now, in this case, the additional information that we were able to gather was specific to the scenario because we were able to recreate the error on demand. Because every time you made a GET request, the put was always erroring out. And so because of that, and because we had access to this environment, we decided to gather information by using the first tool that we're presenting here, which is TCP dump. So what is TCP dump? TCP dump is a packet analyzer that you can use via the command line. There's no GUI, so it can be sort of hard to actually read the information. And so oftentimes what you'll want to do is use TCP dump to capture all of your network traffic and then use another tool to analyze it. The great thing about TCP dump is because you can just use it via the command line, it's really easy to SSH onto a remote server, run TCP dump, capture all of your network traffic, and then move that file to your own machine where you can then analyze it. It's as simple as once you're on the machine that you want to capture traffic for, running a command like tcp dump -w, writing it to an out.pcap file, and then you can specify the interface that you want to be listening to your network traffic on. So in this case, and in most cases, you probably care about the ETH0 interface. Doing so, we are able to gather all of that information by running TCP dump on the HAProxy, on the GoRouter, and on the Diego cells where our applications lived, and then use our next tool, wireshark, to actually analyze all of this network traffic. So what exactly is wireshark, right? Wireshark is an open source packet analyzer with a GUI. So it works really nicely hand in hand with TCP dump. You can actually use wireshark to analyze local traffic in real time, but more often than not, what you'll want to do is capture the traffic to a file and then upload it to wireshark so you have those contents to always be analyzing later if you think that there might be valuable information you missed earlier. Additionally, with wireshark, you can filter and inspect packets, making it easy to follow along and debug. So when you upload a file to wireshark and you start analyzing it, you're going to see something like this. So in this case, we actually filtered on a specific network connection. And so we can see here first, just like the numerical ordering, a timestamp, the source IP, destination IP, protocol, and then number of bytes and additional information about the packet. In this case, what we were looking at is the connection between the Diego cell and HAProxy. And an interesting thing that we noticed here is if we zoom in on this line, we saw that the HAProxy was actually sending a FIN-ACK packet to the Diego cell. So what this means is the HAProxy was closing the connection to the Diego cell, which is unexpected, as this connection has the Diego cell as sort of like, you can think of the client and the HAProxy as the server. Furthermore, immediately after the HAProxy decided to close the connection, we see the Diego cell tried to send a variety of new packets on the same connection. And this is what was causing the put to error out. Because the HAProxy thought that the connection was closed, tried to close it, and the Diego cell wasn't respecting it. Sort of weird, right? But of course, when you're debugging, you're not living in a bubble, you're not living in isolation. There's probably other people who are also trying to debug the problem at hand, are finding out new information and are always sending it your way. And so it would be remiss of us not to give you the full story and tell you at this point in time, we had new information given to us. That disabling keep alives from the GoRouter to the backend fixed the issue. And we were like, what? Disabling keep alives impacts the red arrows here. And we had seen from our TCP dump and wireshark analysis that the actual connection that was failing was connection 5. Like, that's just bizarre. How is it fixing the issue? How is having these keep alives fixing this connection error? At this point, we had gathered a lot of information. And so going back to sort of the steps of the debugging process, we decided to go to our fourth and final step, to come up with a hypothesis and a plan of attack. And to be frank, at this point, we were pretty swayed by the new information that had come in. Like, if something fixes the problem, it seems like a pretty good information nugget to sort of go down the rabbit hole with. And so our first hypothesis was that some value is being propagated from the Go router that made the connection between the HAProxy and front end fail, if changing a value from the Go router fixed the connection between the HAProxy and front end. So again, some value being propagated from the red arrows here was fixing this failing connection. So while we were able to come up with a hypothesis, we weren't able to come up with a plan of attack to either prove or disprove it. We stared forever at these wireshark outputs. And then we said, you know what? We don't know how to move forward with this hypothesis. There's nothing in the logic of any of these systems that we've been staring at that makes it so that this hypothesis would be true. And we can't come up with a way of proving or disproving it. So in line with step 4, we decided to go back to the drawing board and repeat. And this is what you want to do until the root cause is found. So we decided to ignore the new information and say, really, let's focus in on the information that we've gathered from the network traffic and say that something about the HTTP client is causing the closed packet to be ignored. This seems pretty straightforward. It's very in line with the information we had collected and the network traffic we had seen. And again, we don't live in isolation. And as we were debugging this, we got some more information that if they waited 5 seconds between issuing the GET request and the PUT request succeeded. And we were like, 5 seconds, that seems like a timeout. Seems really in line with our new hypothesis that something about the HTTP client is causing the closed packet to be ignored. So we actually asked for it and got access to looking at the application source code to see how they've configured their HTTP client. And they configured it http.get. They used the default HTTP client. It was a Spring Boot app. And so luckily at Pivotal, we have lots of Spring experts in the house. So we went to Slack, went to Google. We're like, wait, is there something about the default client that's doing something weird? And we found out that actually, fun fact, the default HTTP client in Spring ignores FNAC packets from the server. And the default timeout is 5 seconds. And we were further able to confirm this by going back to the configuration we had gathered and saw that the keep alive timeout for the HAProxy was ½ second. So what was happening in this case is that the connection from the front-end application to the HAProxy would be made with the GET request. ½ second later, the HAProxy would decide to close the connection, but the default client wasn't respecting that closed packet and was simply ignoring it, causing the PUT to always error out. By waiting 5 seconds, the client would close the connection, open a new one, and then your PUT would be able to succeed. Solved. So what lessons did we learn? Really, one of the biggest ones was that clients have configuration too. If we had gathered information about the HTTP client and dug into that ahead of time, it may have saved us a couple of days. Because while this is nicely presented to you, it definitely didn't take us a couple of hours to solve this issue. And so we always recommend gathering configuration information about your clients if they're part of your connection path. Additionally, we learned to ignore the red herrings and short-term fixes. The keep alives led us astray, and it was only after we were able to find the root cause that we were then able to go and figure out why keep alives fixed the issue, which was another doozy in and of itself. But we don't have enough time to go into that sidetrack, and so instead I'm going to hand it over to Nitya to talk about the second case study and another way you can approach debugging.
Cool. Thanks, Angela. So now let's look at this other one. So first, let's read the problem statement. Some of the GoRouter instances have high memory usage, and some requests, like cflogin, are unresponsive, and other requests succeed. So first, let's visualize this. Even though we were told that the GoRouter has high memory usage, there are several other components that the cflogin request needs to travel through. So here's a diagram of what the deployment architecture looks like in this case. Requests like cflogin need to travel through the load balancer, through one of the HAProxy instances, through one of the GoRouter instances, until it finally reaches the API. And then the response needs to go back through all of those components to get a response to the client. So now we can start to gather information. We'll start broad and then kind of zoom in as we eliminate possibilities. And so because we know that there's a lot of components at play when handling a request, here's a couple of places that you could look for information, roughly ordered from broad to more focused. And right now, the only information we have relates to high memory usage and cflogin requests hanging. So it's probably a good idea to start broad and look at the VM vitals. So here's a snippet of the VM vitals. This is all stuff that you can get from Bosch, and it can tell you about the health of the VMs. And this snippet happens to be from just router instance 0, and this is one of the VMs that was experiencing the high memory problem. So you can observe here that the memory is high at like 98%, but that the CPU usage is pretty low, around 30%. And another interesting observation is that over time, the memory swap percentage is actually increasing on this router. So we've seen high memory and the memory swapped is increasing over time, so a hypothesis could be that the GoRouter isn't scaled enough, and there aren't enough instances to handle the load. But we also learned from looking around on the other VMs that not all of the router instances see high memory and increasing swap, just a few of them. And in fact, after restarting the router with high memory usage, the problem returns, often on another GoRouter VM. And also the health check endpoints for the load balancer report that the VM is healthy. So we can rule out this hypothesis because one, the CPU usage was fairly low and most of the time was spent waiting. And two, the load balancer health check, those requests are still fine. And so adding more GoRouter instances won't help if traffic is still going to go to those problematic VMs. So now we can start to gather a bit more focused information about the GoRouter by checking the GoRouter logs. And so looking at these logs, one thing sticks out. The GoRouter was having trouble with connections to other components because it was hitting the maximum number of open files. And so we know that open files can be caused by connections that are left open. So which connections, incoming or outgoing, could be causing us to hit this limit? And so let's look at a diagram again to help understand what could cause this. So open files on the GoRouter can be caused by connections from HAProxy to GoRouter, GoRouter to the app backends, or GoRouter to other system components like the API. So all these red arrows could cause us to hit that limit. But there's also one other potential source of open files on the GoRouter, and that's route services. So if you have a route service, the GoRouter, as part of handling the request, will send a request to the route service and wait for that processing to happen before responding to HAProxy. So connection 1 will stay open for as long as the request is being processed in the route service. So gathering information about these connections, we learned that the number of connections between HAProxy and GoRouter is growing, but not GoRouter to the backends. And so that's really helpful. It helps us narrow down to this highlighted arrow as what's increasing. So why might that highlighted arrow grow? We talked about connections from the HAProxy to the GoRouter stay open for as long as GoRouter is processing that request. So when you have a route service, GoRouter has to wait for that route service to do its processing before sending a response. So a slow or misbehaving route service could cause the problem. So that's the next reasonable hypothesis. But we ruled this out by killing slow route services and seeing the problem still persist. And so we're still focused on this highlighted arrow. And since this arrow is concerned with requests going into the GoRouter's access logs can provide us more information about the requests themselves. And from the access logs, we observed many 404s. Not only that, but the 404 request time was much higher than that for other response codes. And so this also fits what we've kind of learned in the problem statement, that our observations that only some of the requests are bottlenecking. So our new hypothesis is that 404s are causing the connections to stay alive. And in order to test our hypothesis, we need to see how GoRouter is actually dealing with these requests. And so we have context from what's happening around the GoRouter, and when choosing a tool to test our 404s hypothesis, we need one that will tell us what's going on inside the GoRouter while the issue is happening. And so pprof is a tool that can help us profile the code so that we can see what's happening inside of GoRouter at this time. It allows you to collect and visualize CPU profiles and other traces and profiles in a Go program. And GoRouter has a pprof endpoint for collecting profile and trace data. And flamegraphs are a way to visualize this data. So we'll look at a flamegraph of profile data for the GoRouter while the problem's happening. So this is a flamegraph of the CPU profile. And I know you can't read the text, but this is what was going on in the GoRouter while the problem was happening. So first, let's talk about how to read a flamegraph. The text in all of these boxes are function names being called in the code. And when you use CPU profiling, the profiler interrupts the program execution at specified intervals and logs the state of the program's call stack. And the length of these boxes tells you how many samples were spent during this profile in this function while this function is executing. So you can very, very roughly think of it as time spent in this function. And so generally, you want to look at the really wide boxes and the last couple of calls in the stack in these wide boxes, because this will tell you what are the last calls in this function stack for a function that took a long time. So there's a lot of samples in this stack. And the interesting part about this stack is it's the one that calls to the logger. So there's some kind of bottleneck in the logging. We know that when profiling this code, there's a lot of 404s, and 404s probably result in logging. And further down the stack, we also see that during the write for the log, it's calling to a locking function. So we finally found our bottleneck, which is lock contention when writing to the disk. So it turns out writing to the disk was the bottleneck. The router attempts to log route unknown for all 404s, which was happening very frequently in this case. And so that could be what caused the connections to persist, because they're stuck waiting to write. And this was verified by isolating a GoRouter VM on an empty hypervisor with no other VMs and seeing the problem go away, because there was no more storage contention. So woo, solved. So here's what we can take away from this case. We looked at a lot of VM metrics at the beginning, but maybe if we had looked at some disk metrics from IOStat, we would have been pointed in the right direction earlier. And it's also useful to start broad and gather as much information as you can, because that gives you more context for when you look at data from tools like pprof. Cool. Now Angela's going to go over some debugging tips.
Cool. So I know we're really close to time, and we're all what's left between you and the hub night out downstairs. So I'm going to go through this super fast. So we covered a lot of tools that you can use and different methodologies for debugging, but we also have some additional general debugging tips. First thing is that we always recommend checking your timeout configurations. In general, you want your load balancer to have the highest timeout, then your Go router, and then your application to have the lowest time. outs. And this is similar to what we saw with case study number 1, where you don't want something further down in your network stack to be closing connections prematurely. We also have some information about logging. First and foremost, application logs have timestamps too, and so you can correlate what's happening in the application with logs in like the Go router or HAProxy. And also you can correlate the access logs in the Go router to the Go router logs themselves by using the VCAP request ID header. Additionally, when in doubt, pull the load balancer out of the equation and ping the Go router directly. This removes just one more network hop and place where a problem could be persisting. We also recommend that in certain scenarios, you might want to test each router individually. And also, certificates are hard, so always check your certs on each level. If you want to look into more depth on any of the tools we talked about in either case study, here are some resources. We'll be having the slides posted soon. And with that, thank you so much. I know we're at time. It was the last session. We really appreciate you being here. And we'll be down here answering questions now, I guess. So thank you.